And is it dx or dy, that kind of thing. So let's do a couple more straightforward examples. Oh yeah, I can remember it's freaking Thursday.
What did we do with the radius?
What's that?
That's part of the radius.
The radius is part of the interval.
The radius was the function.
Oh.
So we took that function and we squared it. Pi r squared.
Okay.
Yeah.
Oh, thank you.
So let's do one with dy, and then we'll do one where the radius, the axis of rotation is different. I'll stop doing that. Let's see. What do you want to do, Jeff? Let's do. You can. You know what, let's just do this. Well, make this that. All right. Just make our y-intercepts easier. What's up, sir? 9. Yes, 9. I don't know how A. I love you guys are like, is A supposed to make it easier? Shit. No, 9. Sorry. So what kind of shape would this be? Well, how do I graph this? It's not upside down. It's sort of. Yes, there you go. Sideways, because the y is being squared now, right? So when y is 3, x is. When y is 3, x is 0, and when y is negative 3, x is 0. So let me say, around the y-axis in the so bordered by this and x equals 0. So I have to tell you what the region is bordered by. So the region is bordered by this shape and x equals 0, which is the y-axis. And how far out does it go here? Yeah, when y is 0, x is 9. I like it. 2, 4, 6, 8. Just like this. So parabolas are nice to start with because they'll be nice and easy to integrate. But now I'm going to rotate this thing around so the cross section, if I draw the mirror image is, oh God, Jeff, let's try this again. That's not too bad for me. Looks like Stewie after an injury. But I'm rotating this thing again, right?
Yeah.
So it's going to be this weird UFO-looking deal. Can you imagine that? This weird sloped thing. I don't know if you guys can see. So if you rotate this thing around. Yes, no? Sort of? Okay. So how am I going to locate a disk? So I'm rotating around the y-axis. Yeah, so at some y position now is going to be my arbitrary disk here, right? So if I'm rotating around the x-axis, I find my disks on the x-axis. If I rotate around the y-axis, I find my disks on the y-axis. So integral dy around the y-axis are parallel to that. Vice versa for x-axis. So I know immediately this is going to be integral dy. Now another little thing. We are going to learn a different method because if I rotated this around this way, it would have to be dx for the disk method. Do you want to solve this thing for y so you have a function of x? And so if I rotate around the x-axis, if I rotate around something parallel to the x-axis, I have to do dx. That's all there is to it. So the function inside has to be a function of x. Can I easily make that a function of x? Not really. I have to break it up into parts, break it up into sections. So there's a whole other method. And in fact, some functions I can't solve for y at all. Go back to implicit differentiation. Some functions I just cannot solve for y. So thank God there is a whole other method that whatever disk method can't do, the other method can do. So together they're able to do everything. Amazing for them. So I have to identify, so basically it's always built off of this. So I got my pi, what's my radius?
Is 9. So that's your function.
What is this?
That's your function.
It's my function, right? It'll be f of y now because it's dy, right? My integral's dy. Why is my integral dy?
Because you're going to
Rotating around the y-axis. So my function has to be of y. That's my f of y. That's my radius. So stay with me. So at 2, if y was 2, how far out is this?
2 minus.
5.
Come on.
5.
Yeah, 9 minus 2 squared is 5. It's 5, isn't it 5?
Yeah.
That's the radius there, isn't it? So this is the radius for any y position. Can you guys see that? Make it a little more concrete for you. Any position you pick, how would I see what the radius is? I would put that y in and see what the x is. So that's the radius. From here to the function, so that is the radius. So that's going to be, that's the radius. And then I have to square it. That's the most commonly made mistake, is to forget that other square. The radius itself has to be squared. You're like, it's already squared. No, it's too bad. So now you just have to FOIL that. I mean, you got to love the level of math required. Now, I'm sorry, what's my limits here?
Negative 3 to 3.
Negative 3 to 3. Now, in this case, does anybody notice?
Could you go to 0?
Yeah, if I did 0 to 3, because why do I know this? It's symmetric. Now, you got to be really careful. There's a few different kinds of symmetry that have to happen, because if my axis was somewhere else, it would no longer be symmetric. And if my interval wasn't itself symmetric, it would no longer be. There's a few different ways, but this is symmetric in every way, so thank God. So you got to be careful about rewriting this as twice from 0 to 3. But in this case, it will work. The top volume has to equal the bottom volume because these regions are symmetric to the axis that they're being rotated around. Maybe. If you're like, I don't know when to do that, then never do it. Never. Just leave it negative 3 to 3. Who cares? It'll come out the same. And then when you FOIL this, what do you get?
81 minus 18y squared plus y
Good. Y4. All right. So 2 pi times
81y
y.
minus 18 over 3y.
Good. 6y squared, right? I remember, I think about it, a 3 needs to be, so it sucks the 3 out, leaves the 6.
Y
cubed, y cubed.
Cube, thank you. I said it and I didn't write it.
1/5 y.
1/5 y5. I love it. That's why you guys are all like, it's okay. And then from 0 to 3 in this case. And now you just got to throw in the 3 there, because for 0 it's going to be 0. So whatever you end up with. And again, we could try to estimate this. And you get whatever you get. Now to make sure that if you feel really good about how you set up your integral, you could put that function in, do second calc number 7, negative 3 to 3, and check. I mean, there's nothing wrong with that. But it doesn't necessarily mean that that's right, because that, you might have made a mistake here. But you can check your integration at least if you just throw that into y1, do second calc number 7. You can always do that.
Negative 2 over 3.
That sounds weird.
Yeah, why?
I don't know. Because it shouldn't
I
be...
forgot that. 81y.
Oh, thank God. Can't be negative volume in this case. Yeah. In fact, the neat thing is no matter where I put this, it's not going to be negative. It can't be. It's just the way it works. Oh, we'll see. So I don't know what you get. It almost doesn't matter what you get there.
8/14.
814? 0.3. Okay. Cool. All right, cool. In my waiting minutes here, I want to do one that's not on the axis itself. It's off axis. Let's see. What would be a nice one to do? Sure.
Six, two.
Okay. Yeah, this is still 6, 2. So y equals x in the first quadrant, rotated around y equals negative 1. So, I should probably, y equals x, and let's say x equals 4. There you go. So it's not open-ended. That would be kind of hard. Infinite volume. So this sucker, 1, 2, 3, 4, 1, 2, 3, 4. So that's the shape I'm talking about, and then I'm going to rotate that. So of course, what shape will I end up with? Cone. It's going to be a cone. It's going to be exactly a cone. So we actually have a geometrical formula we can apply to see if the answer is right at the end. All right, let me stop there for a second. So they have to define the region well enough so you know exactly. Because I could have said between y equals 4 and this, and that would have been this area that I was rotating. Did you guys see that? If I would have said y equals x and y equals 4, that would have been this region I would have been rotated. This triangle would have been rotated. And it would have had a big empty spot in the middle. It would have been this triangle instead. You guys see that?
Yeah.
And then if I rotate it around like this, now of course it's not going to be a cone because I'm offset by 1, but you guys kind of, it would have been a big empty spot in the middle for a couple reasons. A big empty channel down the middle. I don't know if you guys see that. I like it like a bunt cake pan. Doesn't it have a hole all the way through the middle? All right. But it's not that. I didn't say that. I said this. All right. So you do the same thing. What's my radius going to be? So here's my axis. I don't even have to be honest, I don't even have to do the, I was just doing that to see if it would help you see the rotation. But the radius is going to start at the axis and go till it hits the outer edge. Yes, sir?
Wouldn't it be x minus 1? The radius?
No.
It's
How far apart are these?
Like Jay said.
negative.
How far is this? How far is this that?
1, 2,
How far is that?
2.
No. Arbitrary x position. How far is that? Which is
The function.
x, right? So how far is that?
Plus 1.
Plus 1. I like it. Let me let you absorb that. Let me let that sink in. So the radius is always how far the outer edge is from your axis of rotation. So why was it easier earlier? Because I was always going from the 0. So it's going to be whatever the hell that is. Minus 0. Ooh. Now it's going to be whatever the hell that is. Minus negative 1. So it's always the outer edge minus where you started from. That's how you're going to figure out how far apart it really is. Does that make sense? How far apart are two things? You take the difference, right? So my radius in this case is going to be
X.
x plus 1. X minus negative 1. X plus 1. Cool. That's the outer radius. Because what's going to happen with this region? It's going to be... It's going to be empty in there. You see? So here's my shape. Here's my 2D shape. I'm going to rotate that around negative 1. So between 0 and negative 1, there's air. Air, not error, but air, right? So when I rotate that around, it's going to rotate around an empty core. Okay, maybe. So this is still disk method, except I have to subtract this area in here. The volume I end up with, right? So the outer radius is x plus 1. What's the inner radius? So this is the outer radius. What's the inner radius? How far is that from that? 1. Okay. Let that sink in. Let me see if this helps. This has got, you want to bring this back with you because we're going to work with something on the back here. Is that my copy? No, okay.
Let's see if this helps. Okay, most colorful.
Okay. Color. I don't care about Matthew more than what you're drawing.
Oh shit, I'm already way over time.
Way.
So real quick, we'll do this next. But right in the middle there, where it says washers, I hate that they make it sound like it's a different thing. Washers are just outer disk, subtract the inner disks. It's just disks method, where I subtract the middle one. It's sort of like what I call a cookie cutter problem when you had like a trapezoid and you had a circle cut out of it and it said find the area, that shaded area. You just found the area and subtracted. So find this disk and then this disk and then subtract them. That's amazing. So that middle picture I'm hoping might help out a little bit. It's got a little more complicated region, but still, it's got that middle part that's empty. So we'll pick it up next time. Whew.
Not plain.